Welcome to qnawire.
In this question, we're looking at X-ray diffraction right off a surface of a crystal, and the way that the interference actually occurs is because we have multiple rays coming in. Right, we have the first ray reflecting off the surface of the first surface layer, whereas some of them might go down to the second layer right before it reflects off. So as a result of this too, there will be some difference in path that is traveled, which is this path over here, which I'm going to highlight as blue. This is the extra distance that is traveled right by the second ray, right? This ray right travels an extra distance given over here, right? I have not really drawn it very properly, but it's supposed to be symmetric, right, around the center over here, right, around like that. And this extra path difference, right, if it is an integer multiple of the wavelength, then when these two coincide at a very far distance, right, when they meet together, they will have no phase difference, right? They will be in phase with each other, they will have constructive interference, and this will give us a maximum. So what is this path difference? Well, using the angle theta, right, with respect to the central line over here is theta. It means that this distance, if we take this as the distance between two layers of crystal as d, then this distance over here plus this over here will be 2 times of d sine theta. Right, so this is our formula for this electron surface crystal surface diffraction. We're going to use this to find what is the angle theta, where we get our first maximum. Right, that's what we want to find, but we will first need to find what is the wavelength of our electron. So given that it is 71 eV, is the kinetic energy, so it goes to P squared over 2m. You can get the wavelength by h over p, h over square root of 2m times kinetic energy. It's the mass of the electron. The kinetic energy, we have to convert it from eV into joules. Right, and we should get 1.46 times 10 to the power minus 10 meters. Using this, we can find the angle of the first maximum. I'm just putting this in this way. 1 times the wavelength goes to 2 times the crystal separation d times sine theta. So we know the crystal separation, right, is 0.091 nanometers. And therefore theta would be equals to 53.3 degrees. Now the last part of the question asks about what if there is some attractive potential, right, which is the work function of the metal, given as E times phi. Alright, given that this is negative, which means that it's attractive, right, it means that the electron actually will gain energy as it moves closer into the metal. So what happens is that the kinetic energy will increase, right? Or when the electron actually gains this potential energy, and as a result this would lead to a decrease in the wavelength, right? Because this is the formula over here. The wavelength is inversely proportional to square root of the kinetic energy. So if kinetic energy increases, wavelength would decrease. And if with a reduction in the wavelength in this formula, keeping all the rest the same, our theta will definitely decrease, right? Since sine theta will drop, and therefore theta will reduce. Therefore, we will expect that the angle will be smaller.